Huh. Welcome to this open session, interaction session. I always believe that teaching is never complete without a proper avenue of interaction between the students and the teacher. I hope you have gone through all the lecture slides and the video recording of the lectures, and also whatever explanation was given along with the lecture. And then you also took all the questions after after every lecture. We uploaded some 20-25 questions. Now, one of the limitation of this course is that, first of all, I'm not able to see your face. So this eye-to-eye interaction is very, very important. It is certainly a part of the learning process. The other important thing is that I don't get any live questions from you while I'm delivering the lecture. Since I don't get a feedback from you, it's very difficult for me to guess where could be a difficulty or if there is something which needs to be reinforced or repeated or sort of stressed even more, or something could be simply omitted. The most important thing, which I personally feel is one of the biggest limitations, is that in a classroom teaching, we always get a chance to retract, to make corrections. But in a video recording, even if I, by mistake or by simply a slip of tongue or at the spur of the moment, I make a wrong statement or utter a wrong phrase or something, that remains permanently recorded. And I already realized that is, at least in one instance, somebody has pointed out, it certainly has caused some misunderstanding, or so to say, created a wrong impression. That's all the more unfortunate. But the only way we can overcome these limitations is when you are forthright in writing an email or seeking a clarification wherever you have a doubt. One important thing I want to announce is that until L58, we uploaded all the 58 lectures covering the entire length and breadth of the course, and then subsequently we recorded 2 more lectures, 59 and 60, just recently, and I'm told they have already been uploaded. So please go through them, because they are essentially an exercise. First, the 59 was more about the various case studies of surface-initiated failures, and wherein I did point out what kind of surface-dependent property and what kind of evaluation, what kind of testings are important, but most importantly, what are the practical examples of surface-initiated failures and why do they occur, and what could be the possible remedies for them. And always remember that like any other engineering solution, there's hardly a unique solution to a set of problems. Even for a single difficulty or problem in engineering, there could always be multiple solutions, at least multiple approaches of solution. And that's surface engineering also is no exception. So there are several examples where one can do, for example, simply a thin film coating with a PVD or a CVD or a sputtering or an iron plating, or one could do slightly thicker coating. In terms of thicker coating, one can go in the diffusion coating route, or nitriding, carburizing, or maybe some conversion coating. Or each coating has its own merit and demerit. And there are several companies, several industry who actually practice different kinds of approaches depending on their customer satisfaction, their experience, and also on certain local factors like availability and energy cost and transportation ease and so on and so forth. So always remember that in the lectures, even if I have mentioned one particular surface engineering and referred to a specific practical situation, that doesn't mean that another equivalent or a counter solution is not going to be valid at all. So one has to, the job of an engineer, I always maintain, is essentially to find or provide a solution to the existing problems or challenges. And these kind of exercises range anything from designing all the way to failure analysis, and of course include synthesis and testing and so on. So please go through the latest 2 lectures, L59 and L60, which also summarizes the entire range of surface engineering approaches possible, their classification, and different ways of classification, how we can look at it. And then also go through carefully the various failure analysis case studies I have talked about in L59. And I'm told the written sort of the final exam for certificate will be held very soon, end of the week, maybe Saturday or Sunday, April 28 or 29 or 27 or 28 or somewhere, and you must have received the notification. So this is going to be again entirely MCQ type, objective type. Now in this course I purposely avoided giving numerical problems because that would have restricted the time for covering various aspects. So I had to rely upon primarily objective questions, multiple choice. So this pretty much what you already have seen in the end of each of the lectures. So very similar type of questions. Some of the questions may require a little more time, while others would definitely require just. So you can budget something like a minute a question, that kind of a planning. So one has to, if you know, it's very easy. If you don't know, you probably will have to go into the fundamentals and try and relate to the theory behind such a problem posed before you, and you will be able to find the answer because it's very easy. So let me now come to the, I've received a few queries. The first one is from Swapnil Shailendra Deshpande from College of Engineering, Pune, and he has pointed out some very important issues. First of all, the first one relates to lecture 29, plasma nitriding and unimplantation, and the question is about temperature experienced by workpiece during plasma ion implantation or plasma ion immersion process. It's actually plasma immersion ion implantation, or sometimes it's also called plasma surface ion implantation, PSII or PIII, PIII. So plasma immersion ion implantation. And the question is, how do we control the temperature, or what is the level of temperature that is. Now always remember, if you're implanting nitrogen, then it is mechanism wise slightly different, but the basic strengthening mechanism wise same as gas nitriding or plasma nitriding or liquid bath nitriding or even carbonitriding, in all nitrocarburizing. In all these cases, essentially you are implanting nitrogen to push nitrogen into the lattice and create a extended solid solution. Because the nitrogen has very low solubility, immediately it will have a tendency to form nitrides. Now this process is always helped in the presence of temperature, so you need to expose to high temperature. If you don't expose to high temperature, then you will be able to penetrate up to a certain depth and not beyond, because diffusion coefficient at room temperature, even if nitrogen is interstitial, is very low. So you will not be able to create a fairly deep or thick nitrided layer. Now when you say nitrided layer, then you are referring to nitrogen bearing compound formation, which essentially are called iron nitrides or complex nitrides, which can be, for example, the gamma prime nitride or epsilon nitride or zeta nitrides, which we call Fe4n, Fe2 to 3n or Fe2n, or this different stoichiometries. But essentially these are all nitrides and having complex crystal structures, fairly different than the ferrite structure of base iron. And so they are purely incoherent precipitates, and but they are extremely strong and hard, and because of them you actually create very high hardness, wear resistance, and so on. Now, the principal question as to what about the temperature? The temperature is independently controlled. So, there is nothing like you have to maintain that temperature. Higher the better, but then you know very well in nitriding you don't necessarily go to very high temperature, and you restrict somewhere below AC1 temperature. So, typically about 500, 540, not more than 550 degrees centigrade. Even in fact 450 to 540, 530 is the range. So, in case of plasma immersion ion implantation also, you have a separate heater sitting below the sample, and that is that can be independently controlled. So, depending upon the current that you pass through the heating coil, you create temperature inside, and that you can monitor either having a thermocouple directly connected or through some radiative measures. So, from a non-contact mode, you can also measure the temperature. So, the temperature is never taken more than 550 degrees centigrade. So, this is independently controlled. If you don't have any heating arrangement, you still form nitrogen solution, nitrogen bearing solution, and some nitrides, but obviously the case depth will be very small, and you won't achieve the desired hardness and the wear resistance properties. Okay. The next question is from Hari Prasad from IIT Madras, and the first question is regarding assignment. For week 6, the assignment must have been also assignment number 6 and question number 12, and his objection is that the value. So, what is the question is what is the white layer depth? It's assignment 6, question number 6, and this is where he is pointing out that the case depth or the white layer depth, the right answer given was 0.1 to 0.5 millimeter, which if you convert comes to somewhere 0.003 to 0.002 inch. Whereas in the slide that I circulated, you will find a mention about 0.003 to 0.002 inch, which in millimeter scale will be about 0.01 to 0.05. Now, I do agree that the right answer going by the slide or what is written on the slide should have been, the correct answer should have been B, whereas I recommended answer C. The basic reason is, the way when I actually framed the question in a hurry, I didn't want to specify only the white layer. I actually wanted to talk about nitrided layer, and the nitrided layer thickness is actually 0.1 to 0.5. But anyway, that's my mistake. So I'll see what. But the one question is not going to make a hell lot of a difference. So, but you're right, and I do appreciate your keenness in the subject. That in this particular case, I agree. The right answer should have been B. For the next question, same assignment 6, question number 14, the typical hardness of nitride layer in Rockwell C scale can be RC. I gave certain ranges, and the correct answer I indicated would be B, which is RC 55 to 70. And this is correct. I don't know where is the confusion coming from. In the passing, when I make a comment during the lecture, there could always be a certain sentence or a phrase mentioned in some context which probably is not always well articulated. So I didn't hear my own recording, so I don't know what did I exactly say, but 75 Rockwell C is impossible. In fact, 70 is also very rarely seen. You basically, with a diamond indenter, you can measure very high hardness and very low indentation mark, but 75 or that range of Rockwell hardness is very difficult to measure. In fact, there will be deformation or not very correct measurement. So the answer is correct. It should be RC 55 to 70, but I don't know whether during the lecture I did mention 75 or so, but that's not correct. So it should be 55 to 70. So there is another question regarding assignment 7, question number 16. For diffusion coating, vapor pressure of diffusion element should ideally be, this is very, very right. I again thank you for pointing out the mistake. The answer should be A, not B. I don't know how it happened. Must be during the framing of the questions, I thought of A, but then I marked B. This is my mistake, and I do apologize for the mistake. It should be, right answer should be the vapor pressure of the diffuser, otherwise it won't go into vapor state at all. So the diffusant has to have a vapor pressure higher, basically volatile matter, which should be an easy volatilizable material. So the right answer should be A and not B. Then the next question is coming from Lucky, Sant Langwal Institute of Engineering and Technology, Langwal. In electron beam physical vapor deposition, the target material is anode. Actually, PVD doesn't need an electrode. PVD, in fact, there is no electrical circuit in PVD. You basically thermally evaporate something which actually again has a fairly low vapor pressure, will go to vapor state easily, and that too under vacuum the boiling temperature would be reduced, so it can go to vapor state earlier. So once you create that vapor, then by thermal way, by irradiation, by passing a current or whichever way, if you heat and evaporate, the same composition, vapor of the same composition will actually fly through the vacuum and come and sit on top of a cold substrate, which is your substrate. So in this process, there is no need of maintaining any closed electrical circuit. So there is no anode or cathode involved here. Okay. But in the case of electron beam, of course, you emit electrons from the negatively charged electrode, which is a cathode here. So basically, in most of the cases, it's a hot filament cathode which emits electrons. And then you actually have an anode which has a central hole or perforation through which electrons can pass through. Basically, when you energize, they basically have to pass through a more sort of a field which actually accelerate them even more. And so yes, in case of electron beam, you have a negatively charged cathode, and the anode is the target. The target is the anode to which actually the electron hits and causes heating. Okay. In case of sputtering, there is a different exercise altogether. You need actually a cathode because you are going to energize and accelerate argon ion and accelerate them with such a velocity that they can hit this target surface and scoop out atoms from the target. And those atoms, those are atoms, not ions. So those atoms now fly through the vacuum and come and sit on top of a cold substrate. And that's how the coating is formed. So this is called, this is nothing but a physical vapor deposition. But the only thing is, I'm not heating and evaporating the atoms which actually are used for coating. I'm using an electrical circuit and I'm shooting argon ions onto the target surface, and this argon ion with its huge momentum and velocity hits the target surface and then scoop out or eject some of the atoms, neutral atoms, and they actually come and sit and deposit on top of the target. So this is it in case of sputtering. One other question from Uday Bhaskar. Institute name is not given. I would like to understand the wear mechanism of steel in abrasive wear situation. How the wear debris is separating? By which technique the wear debris delamination can be found? See, you have to realize that you're referring to a three-body wear condition. This is possible in abrasive wear. The difference between adhesive and abrasive is that initially you have, in both the cases, you have two counterfaces and you have certain amount of load applied at the contact surface. And because of that, now all the surfaces, both the surfaces, are likely to have certain asperities, roughnesses, and these rough edges actually will interact with each other, and there are two ways they can interact. One is that due to the applied normal pressure, they actually can form temporary cold bonding and can create cold welded joints at these asperities. And then subsequently, they also break off very quickly. So when they break off, then we say this is a loss of material and it amounts to wear. So it amounts to wear through an adhesive wear mechanism. The adhesion between the two surfaces is a temporary, a transient phenomenon. That's through the cold welding, and that is why this kind of material loss is called adhesive wear. On the other hand, when the two rough edges rub against each other and then cause damage to one causes damage to the other, that means one actually causes wearing of material from the other, or machining or chiseling out of material from the other, then we call abrasive wear. So obviously one surface has to be harder than the other, whereas in adhesive wear cases you don't expect too much of a difference in the elastic modulus and hardness of the surfaces. In case of abrasive wear, you necessarily expect one of the surface to be harder, and that is the one which actually cause more of wearing to the other surface. And when it does, then the debris that form can either stay in between and act as sort of a solid lubricant if they are already having some kind of a spherical surface or not so faceted surface. Otherwise, they can be even leave the region, for example, between the two journals of the bearing, if you have a certain amount of lubrication available and flow of lubrication available. So the other question is there any relation between atomic bonding and wear resistance of material? Yes, of course. I mean, the surface mechanical properties are totally dependent upon the bonding characteristics and the strength of the bond. So some material you call hard when you cannot penetrate, when you cannot indent. And you cannot indent a surface with an indenter only when the surface atoms are so tightly bound that they don't deform or they don't allow any loss of material. So there is no crack, no scratch, no indentation formed. And that can happen only when the surface atoms are very tightly bound to each other. So greater the bonding strength of the surfaces, greater will be the wear resistance. But one has to look in totality. This one statement alone should not be considered in isolation. So essentially, it's not just the hardness or the bonding strength alone. You also have to have sufficient ability to absorb mechanical energy, which in other words you call toughness. And this toughness can be also measured in various other ways. So there are multiple aspects one has to take into account. Is fracture toughness influence the wear debris, the wear of debris in abrasive? The sentence is not complete. I understand you're trying to raise a question as to whether fracture toughness has any role in wear resistance. Of course it does. I just now I mentioned that the fracturing leads to wearing. So if the fracturing has to be prevented, that can only be achieved when the bonding strength is higher, or even when the load cycle changes, the amplitude of the load changes, still the material can retain its integrity, or the surface can retain its integrity. So there's no wearing or loss of material. So this is important. Is there any book explaining metallurgical behavior of abrasive wear and influencing properties? It does. There is a very important, what is the name? I'll come back to you. There's a very important book. It must have been mentioned in somewhere during my lecture notes, or maybe initially. There's a famous book. Somehow I'm not able to remember the name. I'll come back to that. Okay. So I've got number of questions here. Let me be quick now. What is the type of wear in high load, high speed bearing materials? Whenever you are talking about wear, you have to realize that you are talking about two counter phases. So it depends on, it's not the speed and the load alone is not sufficient to define what is the type of wear we are talking about. So I assume you are, so also if it's a circular surface or it's a flat surface, that also is very important. If the loading is reciprocating in nature, then you call it a fretting wear. If it's a wear where you have either a round phase or even a flat phase rubbing against the other, and the load is high and also the speed is high, you may expect a abrasive wear in such a situation, provided the contact area is larger. If the contact area is very, very small and if the load application is normal in direction, then it can lead to sort of gouging or some other type of wear. Okay, so this was from Guru Vendra or somebody. Okay, then the next question is from Subodh Rana. What kind of final exam will be? It should be no, it's not going to be subjective. This is going to be entirely objective. I mentioned at the beginning. The final paper also is going to be exactly multiple choice type, the way you have done, and there will be some differences. I think you will have a set of questions which will carry 1 mark each, a set of questions which will carry 2 marks each. So altogether it's a 100 marks question paper, but you require there are altogether maybe 70, not 100, less than 100 questions. So you can budget something like about 1 or 2 minutes per question. That's the kind of, but multiple choice. If you have gone through all the lectures well, it should be fairly easy question paper. Ashish Basu, what are the refrigeration and cooling technique for the turning of satellite coatings? Okay, that it depends. You have to realize that the cooling arrangement on the satellite surface is in a microgravity condition, zero or not zero, but microgravity condition. So you possibly would not be using any coolant which is a fluid, because the fluid dynamics is going to be very different in a microgravity condition. So usually these are phase change materials. So when you are on the brighter side, when you are sun facing side, then certain material property gets activated. In the other side, when you are on the shadow side, then this material is no longer active, so there is no major heat transfer availability possible. Siva Krishna Imani, or can you please tell me some corrosion inhibitors that are used in emulsion? Oh, these are mostly various kinds of organic salts. I won't be able to tell you offhand. In fact, many of these salts are actually what is that, PTAH or something. Anyway, I better not try to guess here lest it creates more confusion in you. You can easily refer to some of the standard places. So Uday Bhaskar, is there the bonding strength difference between carburized steel with 0.8% carbon and melted steel solid solution 0.8 steel, because there is a wear difference between carburized steel with 0.8 without surface treatment? It's a bit confusing. The question is difference between carburized steel, both 0.8% carbon steel. The other one is surface melted steel. Possibly that's what you were trying to say. Now, you have to realize that if it's a carburized steel, 0.8% carbon carburized steel, the strengthening is coming from primarily martensite. When you surface melt, then there's no question of, particularly in plain carbon steel, the hardenability is such that directly cooling from the molten state doesn't fetch you martensite. Instead, you, with so much of carbon, 0.8% carbon, you are likely to end up with a lot more, a large amount of retained austenite. So the wear resistance will be fairly poor. In fact, even poorer, because this austenite not only is softer, but also is metastable. So under loading, under wearing condition, it might undergo a stress-induced martensitic transformation, which might lead to cracking and further wearing. So the strength, the bonding strength, it's not a question of bonding strength alone, because you are talking about a metallic surface and you have a continuum there, free electron cloud there. So there's no question of adhesion of coating with the substrate. It's part of the substrate itself, only the surface microstructure is different, and that is going to be entirely martensitic when you do carburizing, followed by the usual heat treatment, hardening treatment, two-stage hardening treatment, and then you get martensite, so you get higher wear resistance. But when you do surface melting, then you are likely to end up with a lot more volume fraction of retained austenite, which is not a good news, and the wear resistance is not going to be satisfactory. So carburized steel always will have a much higher wear resistance. Okay. Now, how does, again Uday Bhaskar, how does wear of carburized surface in 3-body abrasion? So basically, if you plot the coefficient as a function of either load or time, you'll realize that the characteristic changes when initially it will be faster when you'll have high abrasion reaction or abrasion process happening. You'll reach in between a steady state process when the trapped wear debris will actually act as sort of lubricant between the surfaces, and then subsequently you actually may accumulate so much of debris that they themselves can actually now start acting as abrasives and cause more wear. So now onwards beyond a certain point, so you will see a tertiary level. So pretty much like what we experience in case of creep damages or creep deformation. Very similar 3-stage process, initially fast, then a steady state, finally a much faster exponentially rising state. And that's when the, so it's initially 2-body to 3-body where the debris are acting as lubricants, and then finally the accumulation of debris and particularly having sharp edges can cause further wearing, and you go to further higher state of wearing. Shiva Krishna, can you please explain about emulsion that are used for corrosion inhibitor? I think we already discussed this question. So basically, you actually use inhibitors are agents which actually cause certain protection of the active portion of the surface. So for any corrosion to happen, you require ionic transport, and if you can prevent this kind of easy ionic transport from the surface by way of forming a film, protective film, then the corrosion is inhibited, and that's the role of the inhibitor. Inhibitor can also form a preferential coating on the corrosion, on the corroding substances floating through the substrate. So that can also retard the rate of corrosion. So inhibitors basically or emulsion basically are long organic molecules which actually can coat the corrosion causing agents or provide a film over the surface and then prevent direct ionic transfer, counter ionic transfer. Again Uday Bhaskar, how to calculate fracture toughness in carburized surface? You are not going to treat any different. Normal course, only you have to realize that carburized surface is not a coated surface. Carburized surface is a graded surface. So in terms of carbon concentration, in terms of microstructure, you have certain gradation from surface to the core. So fractures, if you are interested in measuring the fracture toughness, usual way is to use a 3-point or a 4-point bending specimen, since this is a fairly ductile specimen, so even a 3-point is good enough. So you may like to follow the same procedure, create a notch and then subject it to certain bending stresses, and look at the if it is a static loading condition. But if you are willing to measure the fracture toughness under cyclic loading condition, then you have to create just the same way. You create a normal fracture specimen and then create a surface notch. You have a pre-notched specimen and subject to tensile or within the tensile regime, alternating stress cycle, or tensile to compression to tensile and such kind of alternating stress cycle. And then you have to identify where the crack is opening from the notch, and that should be possible to measure through your stress amplitude versus time plot. What is your opinion about the role of self-healing coating in corrosion inhibition? They are good. I mean, self-healing coating is good for corrosion inhibition. So they are very useful material, but by self-healing what you mean is it can be a polymeric substance, or it can be even a solution which can allow precipitation. Now essentially your job, if there is a crack and if there is a sufficient amount of stress around the crack tip, your job is to either close the gap or close the crack, or prevent tensile stress gradient across the crack tip, or mitigate that so that the crack doesn't propagate. So if you have something, some reagent which actually can precipitate and close the gap, or create opposing residual stress at the crack tip, in either way you can stop the crack propagation. So inhibitors in the form of these self-healing coating are nothing but which actually close the gap. So for example, if you have if you see a crack opening and if you can fill it up with some molten metal, if it's a metallic surface, then that certainly will be one such possibility to close the gap, and then you actually raise the life of the surface. Nitriding for non-ferrous bearing metals like ZA alloy and leaded bronze. Okay. Yeah, aluminum zinc, or see, all these non-ferrous systems, whichever is prone to formation of nitride, strong nitrides, certainly are good candidates for nitriding with an intention to improve wear resistance, even in some cases fatigue resistance. Now nitrogen, being a solid, being an interstitial element, actually can go into the solution and then create an extended solid solution. But since the solubility usually is low in iron and also in many other non-ferrous systems like aluminium, titanium and so on, so they are prone to formation of various kinds of nitrides, and when these nitrides form, they actually form a fairly strong, very much harder layer, which actually can prevent easy formation of crack or damages onto the surface. So nitriding is a standard technique, not just for steel, but also very widely applied for all nitriding forming alloys, which are which have carry the solvents like titanium or zirconium or even aluminium and so on. But not so much in copper, not so much in copper bronze. Ajay Kambati, which type of corrosion resistant material is used in space vehicles or in water vehicle like ship, submarine or others? These are two different things altogether. When you are talking about marine atmosphere, your primary enemy is the halide ions, the chlorine. So you wouldn't really design a ship or a large vessel with aluminium or something which has a much lower strength. So usually these are steel and a kind of steel which actually has high strength but not very high alloying elements, because you have to deform, you have to give shape of various complex shapes. For example, if you look at the ship hull, you actually have a very wide and at the same time complex shape. So various forms of high strength low alloy steels are routinely used. So you have to worry about corrosion prevention. Apart from the composition, you also use protections in the form of coatings and even paintings. And even if the steel itself has fairly high cathodic potential, still you would use a good amount of painting to prevent fouling of the biomasses or accumulation of biomasses. You also have the rotating blade, so you would not like any biomasses to accumulate over it, so that the weight changes and then the entire hydrodynamic condition changes. There's another danger, which is hydrogen embrittlement in case of marine environment. That's also something which needs to be prevented, and you generally use low alloying elements which will allow chromium and other useful anti-corrosion elements to be left free in the solution to counteract all these corrosion attacks. And ideally you would like to have fairly low alloying concentration, because otherwise fabricability, weldability and deformability, all these properties are adversely affected. In case of space vehicle, the considerations is entirely high specific strength, low density, high strength, and you don't expect any direct corrosion coming from any of these elements that you encounter either on Earth or in ocean. But on the other hand, you do experience very high frictional forces at the point of launch and also at the point of re-entry, if at all there is a re-entry part involved. So the erosion resistance, frictional erosion at causing high temperature rise at the surface is a very major part. But once you cross the Earth's atmosphere and you are into the rarefied condition, low gravity condition and rarefied, meaning very low air pressure condition, then all these damages or cause of damages are reduced, drastically reduced. You don't experience a lot of wear and tear because of surface damages. Why did you use a different pen? I mean, this is horrible. Use this pen. 70% of the subject, will there be? No, there's no relative grading. This is fairly absolute scoring condition, and so this is just multiple choice question, what you experience in all the assignments. Exactly the same format, but some of the questions will carry 1 mark, some will carry 2 marks. So this is going to be fairly easy exam. About this credit transfer, I'm not sure what is that NPTEL office should be able to give you the right answer. But if you still have a question, you can write an email to me and I'll refer this to NPTEL office. So Shiva Krishna, between RARQ and the units of surface roughness. Average roughness, RA, and you actually will have to refer to the various conditions. Now these are terminology wise, what is not known here is all the roughness indices are length scales basically. So roughness, whether it's average or root mean square or any other form of roughness, essentially these are all length scales. So all the units are units of length scale. I think that is averages over a certain distance. You take the undulations, take the cumulative value and then divide by the length, you get the average. Or else if you take the root mean square is calculated through the statistical means, the way you calculate root mean square. So you take the square and then square addition of the squares, cumulative addition of the squares, and then take the average of that. What else?
In conclusion of this question, the person has asked this question.
But this is I answered already. I'm interested to measure the mechanical properties like tensile and impact and fracture toughness with respect to carburized layer. Okay, you are asking me questions which is probably related to your PhD problem. If you are trying to measure the toughness, surface toughness of the carburized condition, then obviously you have to have a notch created and then carburized. Otherwise, if you create a notch on the carburized surface, then this is a very different condition. In fact, there is no standard technique available for that. But if you wanted to see, again, let me repeat that carburized layer is not a coating. It is just a gradation onto the surface, gradation in terms of composition, in terms of microstructure. So if you want to measure the impact toughness or fracture toughness or some such surface dependent property of the carburized layer, then you should have such a geometry already available, a notch created already, and then do the carburizing treatment and measure the fracture toughness or the impact toughness, whatever you are doing. On the other hand, if you are doing it on a, let's say, a clad surface, then you do the notch onto the clad and then subject it to this kind of a testing. Then you are measuring the fracture toughness of the clad, not the substrate itself. See, when we talk about this residual stress condition, we say it because in case of carburizing, because carbon enters into the surface, expands, and then further expands when it transforms to martensite. So if you already had a notch and if you have now created a carburized layer and then you carry out this bending test or whatever and then measure the fracture toughness, then you are measuring the fracture toughness of the carburized steel. But if you do it on a carburized surface, you don't know exactly what is the depth, and you do not have the same composition along the depth, for a reasonable depth until a reasonable depth. So the notch may actually encounter layers of different composition. Okay, I think if you still need some clarification, this is certainly on I would say questions relate to research problem. So you write a mail and then I'll see if I can talk to you sometime. Any other question? Okay. So essentially I would say that, surface engineering, though surface related damages are always has always been there. I mean, this kind of, it's nothing new. As long as solid materials exist and have faced interaction with forces or environment, various kinds of surface damages have always been there. But somehow the industry is aware of these problems and they do take care through various conventional methods. But the modern approaches of surface engineering is truly recent, is not very, very old. So we don't have a very good textbook available in this. By the by, I actually somehow I can try and locate here. There is a textbook which let me just quickly try to see if I can locate that. It's a fairly well-known book, but for some reason I should be able to tell you. Morton, Fontana. Budinsky. The author's name is K.G. Budinski. It's a Prentice Hall publication, not printed in the recent times. It's 1988 is the version that I have. So it's called Surface Engineering for Wear Resistance, Introduction and Classification of Wear by K.G. Budinsky. Budinski, published by Prentice Hall. Okay, so that's one book which I find very, very useful for wear or surface mechanical interaction of solids. What is tribocorrosion in bearing material? Is it important to be measured, and why research why researchers do more of a dry sliding wear testing for the new materials developed? Well, that's see, first of all, tribocorrosion is again a combined action. Now, in real life, you don't necessarily have always a condition which can be branded as pure corrosion or pure friction or a pure something else. So, when your bearings are subjected to certain, for example, you are using a lubricant. For whatever reason, either the lubricant has degraded or because of various conditions of moisture and other places, the pH has changed. So, let us say it was supposed to be neutral, and now because of degradation of the lubricant, it is having a higher concentration of hydrogen ions or is acting more acidic. So, in such a situation, you are not only having wear or sort of abrasion because of loss of lubricant or degradation of lubricant, you also are having such surface mechanical interaction in presence of aggressive ions. So, that is a tribocorrosion. Now, bearing is one such possibility, but it can happen in any other conditions wherever you have two surfaces in relative motion. In such a situation, you actually have to create a simulated condition if you want to do a testing. So, you do the same wear studies either in a reciprocating condition or in cyclic loading condition, or simply in a rotating condition under a fixed load applied, but in the presence of various concentration of ions, which could be halides, which could be simply higher concentration of hydrogen, or in some cases, if you are interested in creating a basic condition, so more of hydroxyl ions and so on, and then measure the weight loss, measure the dimensional change, and there are also acoustic methods of measuring or monitoring the wear behavior as a function of time. So, these are the ways you can measure. New materials, by developing new materials, essentially we mean materials which can prevent such interactions or mitigate such interactions. So, instead of new materials, I would say that it's a much better approach would be nothing wrong with the existing material. Mostly these difficulties arise because of extraneous factors, but you have to have sufficient protection against such extraneous factors. For example, the lubrication should you should change the lubricant periodically, or you should make sure that even if tribocorrosion condition arises, the surface should not be wear resistant, but also should have properties of corrosion resistance. In fact, we take the example of nitriding as a possible remedy in many cases. And nitrides are both wear resistant, hard, can reduce friction coefficient, and also can provide you decent amount of corrosion resistance, but depends on what substrate we are talking about. So you have to consider what substrate, what is its electrochemical potential, what medium we are talking about, what is the pH level of that medium, and what level of stress applied. Is it regular, irregular, or is it cyclic or reciprocating or linear? So all those factors have to be factored into. Tool wear, measurement of tool wear. The easiest way would be dimensional change or weight change, loss of weight. So if you have a tool which actually is doing some kind of a cutting operation, some machining operation, and you suspect that there is a heavy amount of tool wear, so one easy way would be simply monitor the weight as a function of time without changing the condition. And you can actually do a parametric study. You can vary the load and then see which way the wearing is taking place. And in fact, from the rate of the wear, weight loss as a function of time, from the slope of such weight loss characteristics, you actually can derive a coefficient, and this coefficient can actually give you certain clue as to what kind of failure mechanism is occurring, and if it is really sensitive to load or independent of load. So that can be a very good way of carrying out some systematic research study about the life and performance of a tool, of a cutting tool, or I don't know which kind of a tool you are referring to. But no matter whether it's a cutting operation or shearing operation or polishing operation, you always can use weight loss as a standard index, either weight loss or the displacement, vertical displacement, depending upon what configuration you are using. And correspondingly, you should be able to calibrate and then convert this into a measurable quantity, what you can express. Okay, right. I think so. Probably we are done with all the questions. So if still somebody has some doubts, can always write an email to me, but you have to give me a little more details, not a very sketchy statement which makes it difficult for me to answer. So if you give me all those details, I certainly will come back to you as soon as I can. But the exam is in the coming weekend, I think Saturday or Sunday. So before I wind up, I certainly would like to wish all of you grand success in the exam, and more importantly, I hope on behalf of my colleague Professor Jyotsna Majumder and I, we wish that you would have definitely learned something useful in this course and can very well make use of them in your professional life. Thank you very much, and all the best again.